So the next is module 2. The first thing to look at is pulse code modulation. So here the signal is modulated to convert an analog signal into a binary signal. There's a couple of block diagrams. The first is the modulator, the second is the demodulator. There's not much to look at here except the fact that they exist. Not really sure if you have to draw them, but in case you do, then it's still there. There are a few sources of noise that still occur. They're due to aliasing, quantizing channels, and intersymbol interference. All right, so the first mathematical definition here is the bit rate. So the bit rate is equal to b times fs, where number of bits is b, and the fs is sampling rate, like we already saw. But from the previous module, we also know that the number of bits is given by the logarithm to the base of 2 of L. So from here, we start deriving the quantization error for PCM. So the first thing to do is note that for an input signal, the VP, which is given by the maximum amplitude of the signal, and we have a step size, which is known as delta. So this is the width of the step of your quantization levels. So this is the difference between the maximum amplitude and the minimum amplitude divided by L. So that since one of them is negative, then it becomes 2 VP divided by L, where L is the number of levels. But the second thing we notice, the quantization error value is bound by minus delta by 2 lesser than equal to Q less than equal to delta by 2. So here there's a common question that might show up where they say, here's the percentage of error of your amplitude, find the probability of error or something like that. And usually when they give a 0.02% or something like that, then that basically means Q is delta by 2. So they will give you Q as 0.02%. And then you have to convert that into a decimal. So 0.02% will be 0.0002. That is equivalent to delta by 2, since those are the limits of your quantization error. And then you proceed solving the question like normally, like how you would. And then you have the probability density function, which is given by 1 by delta in these limits of the quantization error and 0 everywhere else. Because it's a zero mean, the quantization noise power, which is the variance. So both of those are the same thing. So the variance eventually slips to delta square divided by 12. So all of this is for derivation purposes. Usually you don't have to do this much, but it's worth knowing anyway where variance comes from. So the variance formula is there, right? The integral of minus delta by 2 to delta by 2. Then you have the q minus mean. Since the mean is 0, then it just becomes q square. And 1 by delta is a constant, so it's taken out. Then it eventually becomes delta square by 12. But we also know that delta is 2 Vp by L, and then we replace L with 2 power B, and then variance eventually becomes Vp square by 3L square. So this is not an important formula per se. It's just a step to keep in mind. Maybe you'll randomly recall it while trying to write a derivation for the exam. So del sigma square is the noise power. Then comes the main part, right? If derive the signal to noise ratio. So here the main formula to remember is the 4.8 plus 6b, and this is in decibels. So there are two kinds of questions you'll get with respect to SNR. The first is they won't specify, they'll just say it's a random input, find the SNR. Then you have to use 4.8 plus 6b, and it's derived because S by N is the ratio of signal power to noise power. As you can see here, we have power divided by NQ and power divided by VP square by 3L square. And then you translate them to 3P by VP square times 2 power 2B. And then you normalize it, it becomes 3 times 2 power 2B. Yeah, the important thing to remember here is that the simple formula A 4.8 plus 6B, and when they say that it's a sinusoidal input, then your expression becomes 1.8 plus 6b, as you see on the top right. So the difference here is just that the magnitude of the real value changes. But also a useful formula to keep in mind is the one on the top right, which is S by N is 3p by Vp square times 2 power 2b, because it can prove useful when they give you the power and ask you to find the signal to noise ratio from that. So the three important formulas to keep in mind from this derivation are that for ordinary inputs, then the signal noise ratio can be 4.8 plus 6b. For sinusoidal inputs, it can be 3p by bp square times 2 power 2b, and decibels this translates to 1.8 plus 6b, where b is the number of bits. So a bit of theory, PCM is robust against noise and interference, overload may appear, requires high attenuation and bandwidth. Few questions. The given bandwidth is 4.2 megahertz. The binary PCM, the number of levels is 512. Find the code word length. Usually this just means the number of bits. The second is transmission bandwidth. The third is final bit rate. And the fourth is signal to noise ratio. It's all simple formulas. Transmission bandwidth is always equal to BW, where they've already given you W. So since we calculate B to be 9 from 512, so it's just log 2 512. Then we get 37.8 megahertz. Bitrate, we already know the formula is BFS, so we get that as well. One more thing to note is that the sampling frequency is always equivalent to 2W. SNR, since it's not specified as a sinusoidal input, it's a binary input instead, then it becomes not binary input. It's a normal input. I don't know what input it is. As long as it's not sinusoidal, I don't care. But the SNR is 4.8 plus 6B. That becomes 38.8 decibels. The second question is PCM system analog wave. So here we see that it is a sinusoidal wave. So no, not really. They haven't said that. But okay, this is a normal wave. Let's not think about that. The accuracy is plus or minus 0.1%. You'll recall that we discussed this just a few seconds ago when we were talking about how the delta by 2 is your error. So waveform is bandwidth 100 hertz and the amplitude range is minus 10 to 10. So the reason this is given is because you now know the VM is equal to plus or minus 10. You have Fs, which is given to you from the bandwidth, which is 2W, it's 200 hertz. The number of bits in each word, we have to find that by calculating delta by 2, because delta by 2 is 0.002. Delta becomes 2 Vp by L, and it's quite simple to calculate delta from that. The third thing asked is the bit rate, which is BFS. We already know that. The minimum absolute channel power is 2800 divided by 2, which is 1400 hertz. I mean, not 2800, that's the bit rate. So the bit rate divided by 2 becomes your frequency, minimum absolute channel. Right. So next question, PCM uses uniform quantizer followed by 7-bit binary encoder. The bitrate is given as 50 times 10 power 6. Find the maximum message bandwidth. As we just saw, the maximum message bandwidth is the same as the minimum message bandwidth. It's R by 2. It's 25 to 10 power 6. The SNR is, um since this is a message signal and it's a sine wave given to us in the frequency of 1 megahertz, we have to use 1.8 plus 6b becomes 43.8 decibels. The next question is the bandwidth of a TV is 4.5 megahertz converted to a PCM bit stream with 1024 quantization levels. Find the bit rate if the sampling rate is 20% above the Nyquist rate. Here we have the number of levels, so we can calculate the number of bits straight away, which is 10 bits. We know that the given W is 4.5 hertz or 4.5 megahertz, sorry. So we can calculate the bit rate, R equals BFS. We also know that the Nyquist rate is 2F max, but they've said that the sampling frequency is 20% above. So we do 1.2 times that, which is 10.8 megahertz. And then your bit rate becomes BFS. Your FS is now 10.8 and your B is 10, so it's 108 MB per second. The next question is your signal bandwidth is 3.5 kilohertz sampled and quantized with a PCM channel transmission of 50 kbps. Find SNR max if VPP is 4V, PRMS is 0.2. This is where the formulas we used in the derivation become useful. So we have P equals VRMS square by R, which is 0.04 watts. We have to assume R equals 1 there because it's normalized. And then we're given that R is 50,000 bits per second. So we calculate number of bits from that to be R by Fs, which is 8 bits. So you actually round it up. So if you get 7.2, 7.0 something, it still rounds up to 8. SNR, the formula we discussed, 3p by bp square times 2 power 2b becomes 1966.08. You convert that into decibels, it becomes 33 decibels. The final two questions are just as straightforward. So here the reverse is asked. The bandwidth of input to PCM is 4 kilohertz. we have VPP, we have the peak amplitudes as 3.8 and minus 3.8. We've given the average power and we give it the SNR as well. They want us to find the number of bits. So here SNR becomes the anti-log of SNR in decibels divided by 10. And then SNR eventually is calculated to be 100. The calculation is written right there. It's pretty simple. And then you use the same formula because you're given power. You have to use the 3p by bp square times 2 power 2b, which is 7 bits. The next question is just a simple substitution for a sinusoidal signal, and you get the answer. All right, DPCM. So encoded signals usually have a lot of redundant information. So to predict this value of present information from previous values, use this predictor then to minimize all of this. So here we have the circuit diagram or the block diagram, I'd say. We have a sampler that takes the input signal and it spits out X of NTS. And then that combines with the predicted signal, which is X cap of NTS in a comparator. So here the positive of the sampler output is taken, the negative of the predictor output is taken. So the comparator one finds the difference between X and X cap. And then this becomes the prediction error, which is known as E of NTS. So E of NTS is X of NTS coming from the sampler minus X cap of NTS coming from the predictor. The error quantized signal is added to this E of NTS, and this is because we want to make sure that the error when you quantize a signal is accounted for. So this is together given into a summer with the output of the predictor to give the signal sum as EQ of NTS equals E of NTS plus Q of NTS. And then finally, we have the encoder output as Q of NTS plus X of NTS. Now, this is just some intuition for the block diagram. The process is far simpler, but yeah, the receiver diagram is right there. This is the prediction filter going back into a feedback loop. The advantage of DPCM is that it requires a far fewer number of quantization levels. Therefore, it requires less bits, and therefore, it's much easier to run this um, DPCM over PCM, for example. So basic improvements, your step size reduces, your quantization error reduces, and therefore, since SNR is inversely proportional, then your SNR increases. Not really important formulas, but just something to keep in mind if they ask you to compare DPCM and PCM. So there are a few sources of error. The first is if the input signal changes so fast that the predicted signal cannot follow it, it is unable to keep track of it, the system noise increases very abruptly, and this is known as slope overloading. So when the predictor signal cannot follow the original input signal, then this is known as slope overloading, and this occurs when your sampling frequency is lesser than the quantity that's given there, which is 2 pi minus 1 AM FM by n minus 1 of delta, where n is equal to the number of pass samples. Usually, when they ask you about slope overloading, they don't usually ask it in DPCM, they ask it in the next category. So I don't think you have to be worried about it right now, but it's useful to keep in mind that slope overloading occurs here as well. So here's an example that should hopefully clear things about DPCM. Probably the only type of question they'll ask from this, which is that the input signal is given by a sequence of 2.1, 2.2, 2.3, 2.6, 2.7, 2.8. And the question asks you to assume the first order prediction filter of x cap of n is x cap x q of n minus 1. And it asks you to give the output of encoding and decoding. So here's what you do. You draw 5 columns, and this is all from the block diagram, if you recall. So X of NTS, X cap of NTS, E of NTS, EQ of NTS, and XQ of NTS. So X of NTS is the given signal, the first column. The second is X cap of NTS. So I'll explain what to do in just a second. But okay, so we can just start at this point. So we have 2.1 as the first X of NTS. And we always take 0 to be the initial value of the predicted signal. So you put 0 in the second column in the first row. So it's 2.1 and 0. E of NTS is the difference between these two signals. So 2.1 minus 0 is 2.1. EQ of NTS is E of NTS rounded to this nearest quantization level. This is the important bit in these types of questions, or probably the only thing that can change. So what they can do is they'll tell you that the frequencies vary from minus 1.75 volts to plus 0.175 plus 1.75 volts. They tell you the step size is 0.5 delta. So, sorry, the delta is zero point 0.5. So what this means is that the signal starts at minus 1.75 and then increases to 1.75 in iterations of zero point 0.5. So the quantization levels are minus 1.75, minus 1.25, minus 0.75, minus 0.25, plus 0.25, plus 0.75, plus 1.25, plus 1.75. So here we have the quantization levels of 0, 1, 2, and then step size is just delta is equal to 1. It's fairly simple, but this is probably the one thing prone to change. So what you have to do in this question particularly is round the 2.1 to the closest quantization level that there is, which is 2, because, well, 2 is the closest one. So the last column is the sum of the second and fourth column, which is x cap of NTS and EQ of NTS, is again relating back to the block diagram that we discussed. So this 2 plus 0 is equal to 2. And then you take this as the new input of x cap of NTS in the next row. So we have 2.22, and then the difference is zero point 0.2, and then here the closest quantization level is 0. So the sum here is 0 plus 2, which is 2, again, which is taken as the input. The difference is zero point 0.3. Again, we have the closest to be 0 because the other side is 1 and it's farther. And here, again, we have 2. The difference is 2.6 minus 2.6. Then here, it's closer to the quantization level 1. So this becomes 2 plus 1, which is 3, which is again taken to the input of the next row. The difference here is minus zero point 0.3. The closest is 0. 3 plus 0 is equal to 3. Again, we have 3. The difference is minus zero point 0.2. The closest is 0 again. So this is 3. So the transmitted DPCM is the column that's EQ of NTS. So that's your quantization level column. So that's the transmitted signal. The 2-bit binary is 100000010000. That's just 2 power 0, 2 power 1 for each bit. Um, that's just standard encoding. So the decoded signal is going to be the second column, which is x cap of NTS. The sampled signal is going to be E of NTS. The quantization error is going to be the difference between the sampled signal and the decoded signal. So this is the only thing that they'll probably ask you. So another example is below that. They've given you here delta is 1 volt, and they've said that this is a mid riser. So this means that your origin is between a rising edge, which means the quantization levels at zero point 0.5, because that's where your quantization starts and ends. So zero point 0.5, then step size is 1. So 0.5, 1.5, minus 0.5, minus 1.5, etc. So here the sequence is 0, 0.3, 1.5, 0.7, 1, 2.3. Again, we start off with the first, which is 0, and then we initialize it with a 0. And then the difference is 0. The closest is zero point 0.5 because there's no quantization level at 0. And then we add the first, second and third, the second and fourth column, which is zero point 0.5. Then the next one we take 1.3, 0.5, the 0.3, 0.5, the difference is minus zero point 0.2. The closest quantization level is minus zero point 0.5 again because there's no zero quantization level. The minus zero point 0.5 plus zero point 0.5 becomes 0 in the last column. And then similarly, you go on down the process. You get the same output. You get the decoder output, you get a quantization error output, and that's pretty much all for DPCM. The next is delta modulation, which only uses 1 bit per sample. So this is to increase correlation between consecutive signals. So the point is that if there is a positive difference between the two, input signal and the staircase approximated signal, then your output becomes 1, otherwise it becomes it's 0. So there's a simple diagram for the modulator and the demodulator that you should probably keep in mind. And they'll probably ask you an advantage or disadvantage if they're feeling very theory uh, oriented, I guess. Okay, so slope over noise, and here's where like it actually matters. So when your staircase approximation cannot follow the message signal, then if you want to avoid this, the value of your delta by TS should be greater than or equal to the maximum of the slope of your input signal. That is not important, but that's just a concept to keep in mind. Granular noise happens when there's a large difference relative to slope characteristics. So the optimal delta is to reduce both of these. Granular noise is essentially the opposite of slope overlap noise, if I'm not mistaken, when message signal is unable to follow the staircase approximation. So here we have the derivation of SNR. So the amplitude maximum in the sinusoidal signal is given by delta fs divided by 2 pi fm. This is also the equivalent amplitude in order to avoid slope overload noise. So to find signal power, we have P is VRMS square by R, P is AM square by 2. So the condition for no slope distortion is delta by 2 pi FM TS. Or you could take that TS up, put the F of S in the numerator, delta FS by 2 pi FM, same thing. So the signal power is then given by, well, the same derivation. You replace P in the original formula, and then you have the same formula for variance, except here the noise power is delta squared by 3. And the only formula that you really need to worry about here is the SNR equals 3fs cubed by 8 pi square W FM square. The way I like to remember it is, well, I just use a woman's feed HS master. The denominator, 8 pi square, is fairly easy to remember. 3 for sure cube, I don't know, something like that in the numerator. There's also a few other useful formulas. Minimum transmission bandwidth is Fs by 2. Bandwidth expansion is Fs by 3W or 2W. Yeah, 2W. So, few questions. Modulator is at 5 times Nyquist for 3 kilohertz bandwidth. Find the maximum amplitude of 2 kilohertz input signal. Step size is 250 millivolts, and we want to avoid slope overload distortion. Again, we use the same formula that we have, right? FFN is 6 kilohertz, W is 3 kilohertz, FS is 30 kilohertz, AM, we plug in the values and we get zero point 0.6 volts. The next question is fairly similar. We have the same condition to avoid slope overload distortion. So I have to rearrange a few inequalities. Then we have SNR. So generally in questions where they don't give you W, which is the bandwidth of the signal itself, you can cancel an f of s in the numerator and it becomes 3fs square by 8 pi square fm square. It's a bit of a variation, I know, but I think this is the only variation I've ever come across, and so you should be fine. Like, just remember fs as similar to w, and when you remove w from the denominator, you have to remove an fs. I don't know the exact math behind this, but that's how it works in the solution. But yeah, so you have that SNR is 11.8 decibels, noise power is delta square by 3, and here limited bandwidth W is not given. Yeah, so look, like I've written there, formula simplification 3fs square by 8 pi square by fm square. Adaptive delta modulation, which is the last thing in this module. So since delta modulation has no control over step size, we have a method which does. So again, a diagram for the block system. Then the numerical here is essentially at a sampling time n, the step size of that particular n is given by the modulus of delta of n minus 1, e of n plus delta of 0 e of n minus 1. So if you're at n equals 0 and your input signal is above your delta modulated signal, so here you'll see a small diagram where there's an analog signal that's just veering upwards and there's a step signal that's like going towards the right. So here you'll notice that um, the black marker is the analog signal. So here the input signal is at a higher point than the delta modulated signal. So we say that delta naught is equal to delta naught, or E naught is tending towards 1. At n equals 1, the signal is lesser than. So since the signal rises to 1, the E1 is lesser than the staircase signal, which means E1 is tending to minus 1. So delta of 1 becomes delta of n minus 1, which is delta of 0, times E of n, which is minus 1 here, because it's lesser than, then plus delta of 0 times E of n minus 1, which is just 1 times delta of 0. So that becomes 0. So as delta is 0, your signal remains the same, which goes from 1 to 2. So for n equals 2, for example, again, it's lesser than the staircase. So your E2 is again tending towards minus 1. So wherever your input signal is lower, at a lower point in amplitude than your staircase signal, then you take minus 1 as your E value. If it's at a higher point, then you take plus 1 as your E value. So essentially, that's how you calculate it. Everywhere you just replace the same formula. Delta of n is the absolute value of delta of n minus 1 times E of n plus delta of 0 times E of n minus 1. It's pretty much it for this module. Usually in DPCM, PCM, and everything, they'll only ask you numericals. So I would not worry too much about the derivations or the block diagrams, but it's useful to keep in mind.